Hi everyone, and welcome to What on Earth? This week, ironically, we're going to be talking about something that's off the Earth, neutron stars. Neutron stars are absolutely amazing. They form from the old dead bodies of burnt out stars, and they're so dense that a teaspoon of them weighs 2 billion tons. In the beginning, we have a star with maybe twice the mass of our own sun. Then, when it uses up all its hydrogen fuel, it goes into a massive explosion called a supernova. Some of the mass is ejected out into interstellar space, but a lot of it remains in the core. Because there's no longer any fusion reaction going on, producing energy and heat and churning the entire thing up, this solar core then collapses in on itself. Remember, this is still a huge mass, well in excess of our own sun, so when the star collapses in on itself, the gravitational field is unbelievably intense, and this is what compacts it down to the densities that I was talking about earlier. But why is it called a neutron star? What's a neutron? Well, you may know from basic chemistry that a neutron is the neutral as a non-electrically charged particle that's found in atomic nuclei. The other ones that are found in atoms are protons and electrons. The protons are positively charged and the electrons are negatively charged. In a normal atom, the protons and neutrons are locked together in a core called the nucleus. The electrons orbit around it, leaving a fair bit of empty space. In a neutron star, however, the gravitational field is so intense it actually collapses the atom. The huge pressure actually forces the electrons into the nucleus of the atom, where they collide with the protons and turn into neutrons. And this entire thing is compacted down so much that all the neutrons that result are actually touching each other. That means, unlike ordinary matter, there's pretty much no space between the particles at all, and that is why it's so dense. In fact, the material of a neutron star is even denser than the nucleus of a normal atom. So a neutron star packs twice the mass of our sun into a very small space, in fact, a sphere that's maybe 20 kilometers across, which is smaller than most cities. This has a couple of really interesting effects. The first of them is that a neutron star spins round unbelievably fast, up to 600 times a second. This is because of something called the conservation of angular momentum. You're already familiar with normal momentum. Angular momentum is just the rotating version of it. The law of conservation of angular momentum states that in an isolated system, angular momentum is always conserved. So what does that mean? Well, if you've ever spun around in an office chair and pulled your arms in to go faster, or maybe watched a figure skater do the same thing, then you've already experienced it for yourself. Now, the further a piece of mass is away from the center of rotation, the greater the angular momentum it has when it's going around at a certain speed. Now, when you pull those arms in, closer to the center of rotation, they need less angular momentum to keep going around at the same speed. But your body still has the same total amount of angular momentum. It hasn't been lost, and you can't create it or destroy it, so this results in a greater rotational speed. Now all stars rotate. For example, our sun rotates once around every 25 days. When the solar core is compacted down into a tiny amount of space, its diameter is reduced by something on the order of 100,000 times, and so correspondingly, the speed of rotation goes up by a similar amount. It accelerates with a vengeance. The other mind-boggling thing is that the escape velocity at the surface of a neutron star is about 1/3 the speed of light, and this means that we can see light that's being emitted from the other side. How's this possible? Say we've got a neutron star here, I'm on this side, and it's emitting light in all directions. Say we take a beam that's coming from this side, on the side away from me. I shouldn't be able to see it, right? Because it's being blocked by the star and it's not coming towards me. Well, the beam of light, when it's coming out, is attracted by the gravitational pull of the neutron star. So it actually starts bending backwards. And the intensity of the field is so strong that it can actually bend the light 180 degrees backwards and send it shooting toward my eyes. So, in this way, I can actually see something that's being blocked from the other side of the star. Isn't that amazing? This has been an introduction into the mind-boggling world of astronomy and neutron stars. Thanks for watching, and remember to spread the science.